So what's a hard drive? A hard drive is a fluid mechanical device that stores binary information on a magnetic disk called a platter. These were the standard for digital storage in computers until the advent of SSDs in the early 2010s. Inside of a hard drive, there's an aluminum platter covered with microscopic granules of magnetic material pictured here. It spins at speeds upwards of 5,400 RPM, while a read and write head hovers only 3 nanometers above, which is about the diameter of a DNA helix. Because that's such a small height, even a tiny speck of dust is enough to damage the data stored on the drive, possibly permanently. So the design of this air bearing, as it's called, is very important. An air bearing exploits the viscous flow of air at low Reynolds numbers to create a tiny lift force on the read and write head, preventing the head from ever directly contacting the platter.
Okay, so in order for us to figure out which governing equations we can use to model the system, we have to do a quick quantitative analysis for the Reynolds number in order to figure out if we can use the viscous flow approximation. So there's our equation for the Reynolds number. These are our values for air. The diameter of our disk is about 3 inches. We use a minimum RPM of 5,500 and a maximum of 7,500. And those values give us a Reynolds number of 0.046 and then a maximum of 0.0608. And in order to follow the approximation, the Reynolds number needs to be much less than 1,000, and both of those are even if you increase the speed drastically or the density or the height between the disk and the head.
Since we are operating under viscous flow assumptions right now, we know that our governing equation is the Navier-Stokes equation. We're going to make a few assumptions about that equation as we work through it. The first being that it is steady state, which is going to take these terms out. We're also going to assume that it's an isobaric system, meaning that the pressure is changing. So we take that through. This assumption is going to change later, so I want you to remember that. That'll happen when we come down here, but for now we're going to take the fact that all of these terms go to 0, and we're going to remember that our viscous force per unit volume is equal to 0. For analyzing the Couette flow, we're going to take two boundary conditions. We're going to assume that there is some velocity on the bottom, uv, and then at the top, again, this is our needle, this is our platter, there is some velocity at the bottom and none at the top. Integrating that twice, we're going to get an expression for the velocity at any point within this channel. Integrating that again, we get the volumetric flow rate in the Couette flow, which is going to come through right here. We're later going to take a superposition of this expression, another expression that we're going to get. So psi flow comes from assuming no longer that it is isobaric, but it is still steady state. So this is still a term. We're going to arrange that, and basically do the same integration. We're going to get a few constants of integration, but taking it through twice and assuming that our boundary conditions are now 0 at the top and bottom, no longer moving on the bottom plate here. Again, the boundary conditions being different isn't super important since it is a superposition of the two. We're going to integrate that second integral again, get the volumetric flow rate in psi flow, which is going to look like this. We're going to take a superposition of these shortly to get the lift force. So if you walk with me real quick here, I'll show you psi flow, where you have parabolic arcs moving through, and the Couette flow, which looks a lot like this. And when we get to our superposition part shortly, it will look a lot like this, which is how we find the lift that acts on the needle. Okay, so using the two expressions for volumetric flow rate that we derived on the back, we're going to rearrange them, sum them up, knowing that they're both equal to a constant. That's the principle of the superposition. We're going to take the integral of that partial with respect to x to get an expression for pressure as it relates to x. Knowing that the boundary conditions on the edges of the plate, the pressure is atmospheric, we can work with one final integral, which is just the pressure integrated with respect to x. If you do this out, you prove that force is greater than 0, positive, which means that the drive does in fact work and lifts the needle above the platter.
So representing our system graphically, we see that we have a linear derivative for the pressure gradient, and which means that our pressure gradient itself will be parabolic, and both sides of it will have ambient pressure. And following conservation of mass, we see that there is a higher mass flow rate on the left edge than on the right edge of the needle. And here you can see the ambient pressure on both sides, and following the profile of the gradient, the highest pressure is found in the middle, while on the edges it reaches ambient pressure. And this follows, this is like a combination or a superposition of Couette and Basel flow, which gives you the profile one.